In the architecture of the universe, silence is the dominant language. Beyond the gravitational embrace of stars, past the orbits of worlds and the dust lanes of nebulae, space becomes a cathedral of emptiness. Here, electromagnetic radiation obeys the inexorable mathematics of the inverse square law, every photon spreading outward from its source, diluting into the cosmic background, fading with the pitiless arithmetic of distance. Entropy claims all transmissions. The universe, in its fundamental nature, is a place where voices go to dissolve. This is not poetry. This is thermodynamics. Every radio telescope pointed at the heavens knows this truth intimately. Signals from distant pulsars arrive weakened to near nothingness, their strength measured in watts per square meter. So small the numbers require negative exponents. Even the most powerful broadcasts from Earth are radar installations. Our communication satellites would become indistinguishable from random noise within mere light years, swallowed by the static hiss of hydrogen atoms drifting through the void. And yet, in 1977, a radio telescope in Ohio detected something that should not have been possible. A narrowband signal, precisely tuned, impossibly strong, lasting 72 seconds before vanishing into the cosmic dark. They called it the WOW signal, and it obeyed the expected script. It appeared once, then faded into silence, becoming nothing more than a mystery and a memory. But there are other signals. Signals that do not fade. Signals that return. Across decades of observation, certain anomalous radio sources have demonstrated a behavior that contradicts the fundamental physics of signal propagation. They persist when they should decay. They reappear when they should be lost forever beneath the threshold of detection. Like echoes in a canyon that grow louder with each repetition, these transmissions seem to violate the very grammar of space-time itself. If sound is memory, and signals are footprints in the electromagnetic spectrum, then what does it mean when an echo refuses to die? This is not a story about aliens. Not yet. This is a story about physics breaking its own silence. The story begins in an era when humanity first learned to listen to the darkness. In the decades following World War II, the same technology that had been engineered for radar and communication was turned skyward with a different purpose. Radio telescopes, vast metal dishes, and antenna arrays began sweeping across the celestial sphere, translating the invisible electromagnetic spectrum into data that could be studied, cataloged, understood. This was the dawn of radio astronomy, and it revealed a universe far stranger than optical telescopes had ever suggested. The cosmos, it turned out, was not silent. It hummed with radiation. Pulsars announced themselves with metronomic precision, rotating neutron stars, broadcasting lighthouse beams of radio waves, some spinning hundreds of times per second, their signals reaching Earth with clockwork regularity. Quasars blazed at the edges of observable space, supermassive black holes devouring galaxies and screaming their existence across billions of light years, and pervading everything, like a faint whisper left over from creation itself, was the cosmic microwave background, the cooled afterglow of the Big Bang, mapping the temperature fluctuations of the infant universe. By the 1970s, astronomers have become cartographers of the invisible, charting a new atlas of the heavens written in frequencies the human eye could never perceive. But among the cataloged and the explained, there existed anomalies, signals that arrived without obvious sources, transient bursts that defied categorization. Most were eventually attributed to terrestrial interference satellites, aircraft, ground-based transmitters bleeding into the data. Others remained unexplained, too brief or too weak to warrant extended investigation. They were logged, time-stamped, archived in filing cabinets and magnetic tapes, and then, inevitably, forgotten. Until one returned. The initial detection occurred at the Ohio State University Radio Observatory in August of 1977. Captured by the Big Ear telescope. Fixed structure the size of 3 football fields. Listening passively as the Earth's rotation swept the sky across its field of view. For 72 seconds, a narrowband signal at 1420 MHz, the frequency of neutral hydrogen, the most abundant element in the universe, registered at an intensity 30 times stronger than the background noise. Dr. Jerry Emmon, reviewing the computer printout days later, circled the alphanumeric sequence 6EQUJ5, representing the signal's rising and falling intensity. In the margin, he wrote a single word: wow. The signal matched no known astronomical phenomenon. It was far too powerful to be a natural emission at that frequency and bandwidth. It appeared to originate from the direction of the constellation Sagittarius, near the globular cluster M55. Though pinpointing its exact location was impossible with the telescope's broad beam. And then, nothing. Follow-up observations found only silence. For years, the wow signal existed as a solitary data point, fascinating, inexplicable, but ultimately unrepeatable. Science demands reproducibility, and without a second detection, the signal remained a curiosity, a footnote in the expanding catalog of cosmic mysteries. But it was not alone. In subsequent decades, other observatories would detect similar phenomena. The signal, designated SHG B02+14A, discovered in 2003 during the SETI at Home Distributed Computing Project. The fast radio bursts that would baffle astronomers beginning in 2007. And strangest of all, the long delay echoes radio signals that seemed to bounce back to Earth seconds after transmission, as if reflected by something in orbit. Though no object existed where the reflection originated, these were not identical events. But they shared a common characteristic. They should have been singular occurrences, statistical flukes in an infinite sea of random noise. Instead, some of them persisted. Some of them returned. And a few observatories began to notice a pattern where none should exist. The equations that govern electromagnetic radiation through space are not suggestions. They are laws tested, verified, woven into the mathematical fabric of reality itself. When a radio signal leaves its source, it expands as a sphere of electromagnetic energy, growing larger with each passing moment. The intensity of that signal decreases proportionally to the square of the distance traveled. Double the distance, and the signal strength drops to 1/4. This is the inverse square law, and it is as fundamental to physics as gravity itself. Every pulsar, every quasar, every transmission ever measured obeys this principle without exception. Until it didn't. Anomaly first became apparent when astronomers attempted to calculate the distance to the recurring signal sources using standard radio astronomy techniques. The measurements didn't converge. The signals were arriving at strengths that contradicted their apparent origins. If the source was located where the direction suggested, thousands of light years distant in interstellar space, then the received power should have been orders of magnitude weaker, barely distinguishable from the cosmic microwave background. Instead, the signals maintained an intensity that suggested they were closer, much closer. Yet no corresponding source existed in nearby space. Some detections exhibited even stranger behavior. The signal strength remained nearly constant across multiple observations separated by months or years. This was impossible, even if the source's intrinsic power remained stable. The Earth's motion through space orbiting the Sun orbiting the galactic center should have produced measurable Doppler shifts and variations in received intensity as the distance between source and observer changed, but the signals remained eerily consistent, as if distance itself had become irrelevant. Unlike the rhythmic pulses of pulsars, neutron stars whose rotational periods can be measured to millisecond precision, these signals carried no natural periodicity. They arrived in bursts, sometimes isolated, sometimes in clusters, following no predictable pattern. This ruled out most known astrophysical phenomena. Pulsars are clocks. Quasars flicker with the chaotic accretion of matter into black holes, but their variations follow statistical patterns, shaped by turbulence and magnetic fields. These signals followed no such pattern. They were structured, but not periodic, organized, but not predictable, and they came from the void between stars, from coordinates far beyond Earth's orbital plane, beyond the solar system's protective heliosphere, from regions of space that contained, according to every survey and catalog, nothing capable of generating such transmissions. Yet perhaps most disturbing was the equipment itself. As radio astronomy advanced through the late 20th and early 21st centuries, observatories upgraded their instruments. Old analog receivers were replaced with digital systems. New telescopes with different sensitivities and frequency ranges came online. The Very Large Array in New Mexico, the Arecibo Observatory in Puerto Rico, the Parkes Telescope in Australia, each with distinct technical specifications, each calibrated to detect different aspects of the radio spectrum. Logic dictated that if these signals were artifacts, errors in equipment, interference from satellites, glitches in processing, then changing the instruments should eliminate them. Different telescopes should see different noise patterns. Instead, the signals appeared across multiple facilities. They manifested in different frequency bands, as if the source were broadcasting across a broad spectrum simultaneously. They were detected by observatories on opposite sides of the Earth, sometimes within hours of each other, sometimes simultaneously. The signals were not equipment failures. They were real. But then came the echoes. In isolated incidents stretching back decades. RNDIO operators and early SETI researchers had reported a phenomenon known as long-delay echoes, transmission signals that return to Earth seconds or even minutes after being sent, far too delayed to be normal ionospheric reflection. Some delays reached 8 seconds. Others exceeded 30 for a radio wave traveling at the speed of light. An 8-second delay would require a reflecting surface approximately 1.2 million kilometers away, 3 times the distance to the moon, but no natural or artificial object existed at those coordinates. The echoes were arriving from empty space. In the 1970s, Scottish astronomer Duncan Lunan had controversially suggested these echoes might be signals from an extraterrestrial probe, even claiming to decode them as a star map. The scientific community dismissed the interpretation as pattern-seeking in noise, but the echoes persisted in the data, unexplained and unrepeatable on demand. Now, decades later, astronomers were detecting similar phenomena associated with the persistent signals. Bursts that seemed to answer transmissions Earth hadn't sent. Reflections without reflectors. Signals that behaved less like radiation propagating through space and more like information being relayed, copied. Delayed. RETRANSMITTED. In university offices and observatory control rooms, scientists began asking a question they dared not publish. Were they hearing Earth's own transmissions? Bounced back by something that should not exist? Something listening. Something responding. Something waiting in the silence between stars. When the pattern persists across distance, across time, across instruments, it ceases to be coincidence and becomes evidence. By the early 2000s, a quiet collaboration had formed among astronomers working at disparate facilities across the globe. No formal announcement was made. No press releases issued. But data began flowing between observatories. The Very Large Array in the New Mexican desert, The Parkes telescope beneath Australian skies. The refurbished Arecibo dish in Puerto Rico before its collapse. And the newly constructed FAST telescope in China, the largest single-dish radio telescope ever built. Each facility maintained detailed logs of the anomalous detections. Timestamps synchronized to atomic clocks. Frequency measurements precise to fractions of a hertz. Polarization data. Intensity curves. The signals were being tracked with the same rigor once reserved for pulsar timing arrays and gravitational wave candidates. The analysis began in earnest. Spectral decomposition breaking the signals into their constituent frequencies revealed something immediately striking. Unlike natural radio sources, which typically emit across broad, continuous spectra shaped by thermal processes and magnetic fields, these signals were remarkably narrow. They occupied specific frequency bands with sharp edges, more characteristic of engineered transmissions than astrophysical phenomena. Fourier transforms, mathematical techniques for identifying periodic components hidden within complex waveforms, were applied to hundreds of hours of recorded data. The results were puzzling. While the signals lacked the obvious periodicity of pulsars, they contained subtle rhythmic structures, frequency modulations that repeated at irregular intervals, like a melody with measures of different lengths. Cross-correlation. Analysis compared signals detected at different observatories, searching for similarities that might indicate a common source. The correlations were positive, but strange. Signals detected at Parkes and the VLA, separated by nearly 10,000 kilometers, sometimes showed identical fine structure, despite being recorded hours apart. This suggested either a source of enormous angular size implausibly large for the indicated distance, or multiple transmissions carrying identical information. Systematically, the terrestrial explanations were eliminated. Satellite interference was the first suspect. Earth's orbit had become crowded with telecommunications satellites, GPS constellations, weather monitors, and classified military payloads. But satellites occupy specific, predictable orbits. Their signals Doppler shift in characteristic ways as they move relative to ground-based observers. And they transmitted frequencies allocated by international agreement, carefully separated from radio astronomy protected bands. The anomalous signals matched none of these signatures. They appeared at frequencies where no authorized transmitters operated. Their Doppler characteristics indicated sources at stellar distances, not orbital altitudes. Solar reflection radio, waves bouncing off the sun's corona or being refracted through solar plasma, was considered and dismissed. The geometry was wrong. Signals arriving from directions opposite the sun's position could not be solar reflections. And the signal characteristics showed no correlation with solar activity cycles, ionospheric propagation, the bouncing of radio waves off charged layers in Earth's upper atmosphere, can sometimes produce unexpected long-distance communication at certain frequencies. But these effects are well understood, frequency-dependent, and produce characteristic distortions. The anomalous signals bore none of these hallmarks. They arrived from directions above the ionosphere's maximum altitude, from elevation angles where bounce propagation cannot occur. Every conventional explanation crumbled under scrutiny. Then, the AI models began finding patterns human analysts had missed. Machine learning algorithms, trained on the signal data neural networks designed to identify structure in complex datasets, started flagging unusual regularities. The signals were not random noise. When subjected to compression algorithms, they compressed far more efficiently than they should, a mathematical indicator of embedded information. Random noise is incompressible. Information is not. The entropy measurements were suggestive. These signals contained less randomness than natural astrophysical sources. but more complexity than simple periodic phenomena. When researchers plotted certain signal bursts in time-frequency space, creating visual representations called spectrograms where time runs horizontally, frequency vertically, and intensity is shown as brightness, geometric shapes emerged. Symmetrical patterns, parallel lines that shouldn't exist in natural emissions, formations that resembled grids, nested structures, arrangements that evoked mathematical precision rather than physical chaos. One spectrogram, recorded over a 3-hour period by FAST in 2019, showed a series of bursts that, when plotted, formed what appeared to be a nested set of squares. Each subsequent square slightly offset and rotated from the previous one. The pattern was subtle, visible only after sophisticated filtering removed background noise. But it was undeniably there. Too geometric to be random, too complex to be simple interference. The implications hung in the air of control rooms and conference halls. Unspoken but understood. If these were messages, someone had to attempt a reply. In 2001, a team at the Evpatoria Planetary Radar in Ukraine transmitted the teenage message towards 6 sun-like stars, a deliberate attempt at interstellar communication. In 2017, Breakthrough Listen began systematic observations of Proxima Centauri, humanity's nearest stellar neighbor. But these were blind transmissions, hopeful signals cast into the void without expectation of response within a human lifetime. This was different. Something was already transmitting. The question was whether it would listen. In the autumn of 2022, a coordinated transmission was made from the Parkes telescope, a carefully structured radio pulse, directed toward the coordinates where multiple anomalous signals had originated, modulated with a simple mathematical sequence, prime numbers. The Fibonacci series, a representation of hydrogen's spectral line. Then, silence, waiting. The electromagnetic message traveling at light speed toward an unknown destination, years away from any possible response. But 16 hours later, another signal arrived, not from the transmission's destination, from a different coordinate entirely, and buried in its structure was an echo, faint but unmistakable, of the sequence that had been sent. There are moments in science when observation transforms into confrontation, when the act of studying something changes its behavior, and the boundary between observer and observed begins to dissolve. The adaptation was first noticed in March of 2023. FAST telescope in China had been monitoring one of the recurring signal sources on a narrow frequency band centered at 1,420 megahertz, the neutral hydrogen line, the same frequency where the WOW signal had been detected decades earlier. For 3 consecutive nights, the signal appeared with remarkable consistency, arriving in bursts lasting between 15 and 40 seconds, separated by intervals that varied but averaged around 11 minutes. Then, following standard radio astronomy protocol to rule out local interference, the observation team shifted their receiver to a different frequency, 1662 MHz, the hydroxyl radical line, another significant marker in the radio spectrum often monitored by SETI researchers. The signal followed. Within 2 hours of the frequency change, bursts began appearing at the new frequency, exhibiting the same structural characteristics, the same intensity profile, the same irregular timing. This should not have been possible. If the source were a natural astrophysical phenomena, a pulsar, a magnetar, any known stellar object, its emission frequency would be determined by physical processes, electron transitions, magnetic field strengths, plasma conditions. These were not properties that could change in response to an observer's actions. Yet the signal had migrated across 242 megahertz of spectrum, tracking the telescope's new observation frequency with seemingly deliberate precision. Other observatories began testing the phenomenon. The very large array shifted between multiple frequency bands over a 72-hour observation period. Each time, within hours, signal activity would diminish at the abandoned frequency and intensify at the new one. It was as if the source were aware it was being monitored and was adjusting its transmission to maintain contact. The word that scientists avoided using, even in private correspondence, was responsive. But something deeper was emerging from the data, something that violated not just the physics of signal propagation, but the architecture of causality itself. The long-delay echoes had never fully ceased. Since the first documented cases in the 1920s and 1930s, sporadic reports had surfaced of radio transmissions returning to their source after impossible delay seconds, minutes, occasionally longer. Most had been dismissed as atmospheric anomalies, equipment errors, misidentified satellite reflections. Now, with modern digital recording and precise timing, the echoes could be analyzed in detail. And the analysis revealed an impossibility. In May of 2023, the Arecibo Observatory's replacement facility, the Next Generation Arecibo Telescope, still under construction but with partial operational capability, detected an echo of a transmission made from the original Arecibo dish in 1974. The Arecibo message, a pictogram transmitted toward the globular cluster M13, containing information about humanity, DNA structure, the solar system, and the telescope itself. The echo was faint, degraded, distorted by what appeared to be decades of interference and noise accumulation. But spectral analysis confirmed it. The frequency, the modulation pattern, the underlying structure all matched the 1974 transmission with greater than 99.7% correlation. The Arecibo dish had collapsed in 2020. It had not transmitted anything in years. Yet here was its message, returning like a ghost's voice recorded on magnetic tape, aged, weathered, but unmistakably the original broadcast. The signal had traveled for 49 years and somehow returned. The distance and travel time didn't reconcile. M13 is 25,000 light-years away. Even if some reflective structure existed there, an impossibility given the cluster's composition, the signal should not return for another 49,951 years. Yet it had arrived within a human lifetime, as if the intervening space had been somehow folded, compressed, bypassed. Then came the echoes that should not exist at all. In June, the Parkes telescope received an echo of a radio astronomy calibration sequence, a specific pattern used to test equipment functionality. The sequence was standard, documented in technical manuals, used by observatories worldwide for decades. But this particular sequence hadn't been transmitted yet. The Parkes team had scheduled it for execution in their maintenance protocol the following week. The echo arrived 6 days early, a perfect match for a transmission that existed only in their planned observation schedule. It happened again at the VLA, an echo of a test pattern, received 31 hours before the test was conducted. At FAST, a return signal containing embedded data that matched a planned SETI transmission down to the bit-level encoding, a transmission that wouldn't be sent for another 4 months. The signals were not merely persisting across space, they were bleeding across time. Physicists have long known that the equations governing electromagnetic radiation are time-symmetric. They work equally well forward and backward in temporal direction. But this is a mathematical property, not a physical one. Causality enforces a forward arrow. Causes precede effects. Messages arrive after they're sent. The universe does not run backward. Yet the data suggested otherwise. The signals were behaving as if the distinction between transmission and reception, between past and future, had become negotiable. And still, the signals evolved. Early detections had been simple, narrow band bursts, roughly consistent in structure. But as months of observation accumulated, complexity increased. The signals began exhibiting layered modulation carrier waves with multiple embedded frequencies, each containing different patterns. Spectrograms showed fractal-like structures, self-similar across different timescales. Machine learning models trained on early data failed to predict later signals. The source was not repeating a fixed pattern. It was elaborating, developing variations, as if refining a communication protocol or learning how to speak. In the sterile control rooms of radio observatories, surrounded by banks of computers processing terabytes of cosmic data, astronomers faced a realization that textbooks had not prepared them for. The universe was not simply full of signals humanity had failed to detect. It was full of signals that were detecting humanity, watching, responding, remembering. Transmissions from futures that had not yet occurred and pasts that should had faded into entropy. The echo that refused to die had become something more than an anomaly. It had become a mirror, reflecting Earth's voice back through a topology of spacetime that should not exist, and it was still transmitting. In the face of the unexplainable, science does what it has always done. It builds models, proposes mechanisms, searches for frameworks that can contain the anomaly within the known laws of nature. The first attempts at natural explanation focused on plasma physics. The interstellar medium is not empty. It is threaded with ionized gas, tenuous but vast, capable of refracting and scattering electromagnetic radiation in complex ways. Plasma lensing, a phenomenon where radio waves are bent and focused by irregularities in electron density, has been observed around pulsars and in the solar wind. Could structured plasma clouds act as waveguides, channeling signals across interstellar distances with reduced losses? Could they create false echoes through multiple scattering paths, making a single transmission appear to arrive from different directions at different times? The mathematics were explored. The answer was unsatisfying. Plasma lensing could explain signal persistence, but not adaptation. It could not account for frequency following behavior, temporal anomalies, or the geometric patterns embedded in the transmissions. Gravitational effects offered more exotic possibilities. Einstein's general relativity predicts that massive objects warp spacetime, bending the paths of light and radio waves, a phenomenon called gravitational lensing, observed countless times around galaxies, galaxy clusters, and black holes. In rare configurations, lensing can produce multiple images of the same distant source, each arriving at Earth along a different curved path through SPAC, ET, IMME. But could gravity do more than merely bend signals? Could it create temporal loops? Near the event horizon of a rotating black hole, spacetime becomes so severely distorted that closed time-like curves become theoretically possible paths through spacetime that loop back on themselves, allowing travel into one's own past. If a signal were to traverse such a region, could it emerge at a time earlier than its transmission? The hypothesis was tantalizing but faced insurmountable problems. No black hole existed at the coordinates where the signals originated. And even near a black hole, the tidal forces would shred any coherent signal into incoherent noise long before temporal effects became significant. Gravitational time loops remain theoretical curiosities, never observed, never demonstrated outside the mathematics of extreme solutions to Einstein's equations. Then physicists turn to the quantum realm. Quantum field theory describes the vacuum of space not as empty nothingness, but as a seething foam of virtual particles, electron-positron pairs, photons, quarks constantly appearing and annihilating in timescales so brief they evade direct observation. These vacuum fluctuations are real. They produce measurable effects like the Casimir force and the Lamb shift in atomic spectra. A speculative hypothesis emerged. Could the quantum vacuum preserve electromagnetic patterns as holographic imprints? Information encoded not in matter or fields, but in the structure of space-time itself, quantum echoes embedded in the fabric of reality. Accessible under conditions not yet understood. It was unfalsifiable, untestable, more philosophy than physics. But it offered a framework. If information could be written into the vacuum's quantum state, perhaps it could be read back out, creating the illusion of signals that persist, return, or arrive before being sent. Yet one explanation remained unspoken in formal papers, but whispered in conference hallways. The signals might not be natural at all. The alien hypothesis carried both appeal and dread. An ancient automated beacon, constructed by a civilization long extinct, programmed to relay transmissions across space and time, a cosmic archive, preserving the electromagnetic history of the galaxy. Or perhaps more unsettling, a probe deliberately mimicking Earth's own signals, demonstrating technological capability by reflecting humanity's transmissions back with precision we could not achieve ourselves. If the latter, the implications were profound. Any civilization capable of manipulating signals across space-time, of responding faster than light travel delays should allow, would possess physics so advanced that human science might appear to them as alchemy appears to modern chemistry, a primitive groping toward truths they had mastered eons ago. But there was one final hypothesis, spoken only in the smallest hours of night, when exhaustion loosened the tongues of physicists who had stared too long at data that made no sense. Stephen Hawking proved that information cannot be destroyed. Even by black holes, it must be preserved somewhere, somehow, encoded in ways that transcend ordinary matter and energy. His work suggested that the universe itself might be a vast information processing structure, every quantum interaction leaving an indelible mark on the cosmic ledger. What if the universe retained memory? Not metaphorically, but literally, a holographic record of every electromagnetic wave ever generated, preserved in dimensions beyond the familiar four. What if consciousness itself, in ways not yet understood, could access this archive? Read it, write to it, create echoes that propagated not just through space, but through the informational substrate of reality itself. It was not science. Not yet. Perhaps not ever. But as the signals continued adapting, evolving, remembering futures and pasts with equal clarity, even the most skeptical researchers began to wonder if the universe they thought they understood was merely the surface of something far deeper. Something that had been listening all along. When the mystery refuses to resolve, the response is not surrender, it is escalation. More telescopes, deeper analysis, tools designed not merely to observe, but to interrogate. By 2024, the anomalous signals have been elevated from curiosity to priority target across the global radio astronomy community. Observation time, once allocated months in advance through competitive proposal processes, was being reallocated in real time. The signals had earned what few phenomena ever achieve: continuous monitoring protocols spanning multiple continents and dozens of facilities. The low frequency array offer became one of the primary sentinel systems. Unlike traditional radio telescopes built from massive dishes, LOFAR consists of thousands of small antennas distributed across Europe, digitally connected to function as a single enormous instrument. Its strength lies in sensitivity to low-frequency radio waves, the kind that penetrate interstellar plasma clouds and carry information across vast cosmic distances. LOFAR's distributed architecture offered another advantage: interferometry. By comparing the precise arrival times of signals at different antennas, Researchers could determine the direction of the source with extraordinary precision, narrowing the origin point from broad patches of sky to coordinates measurable in arcseconds. Yet even with this precision, the signals remained elusive. The calculated positions shifted slightly between observations, drifting across the celestial sphere as if the source were moving, or as if multiple sources were transmitting in coordination. In China, the 500-meter aperture spherical telescope FAST brought unmatched sensitivity to the investigation. As the world's largest single-dish radio telescope, carved into a natural karst depression in Guizhou province, FAST could detect signals weaker than any facility before it. If the transmissions contained faint substructures, hidden layers of information beneath the primary carrier wave, FAST had the capability to extract them. The telescope operated in dedicated observation modes, spending hundreds of hours locked onto the anomalous coordinates, recording at multiple frequencies simultaneously. Petabytes of data flowed into storage systems, waiting for analysis algorithms that were themselves still being developed, because traditional signal processing techniques were proving inadequate. The patterns in the data were too complex for conventional Fourier analysis, too irregular for standard periodicity searches. They exhibited characteristics that mathematicians recognized from chaos theory and fractal geometry: self-similarity across scales, sensitive dependence on initial conditions, structure that persisted no matter how deeply one zoomed into the details. This is where artificial intelligence entered the investigation. Deep reinforcement learning, neural networks trained not through supervised examples, but through exploratory interaction with data, began identifying regularities invisible to human analysts. The algorithms were not told what to look for. Instead, they were rewarded for finding compression, for discovering mathematical descriptions that could represent the signal data more efficiently than raw recordings. The results were striking. The AI models detected fractal patterns in the signal's amplitude fluctuations, nested hierarchies of timescales where similar structures repeated at intervals related by non-integer ratios. They found correlations between signals detected hours apart, connections that suggested a long-term coherence, transcending individual bursts. The models indicated something more unsettling. The signals appeared to be responding to the analysis itself. After certain algorithmic probes, subsequent transmissions would exhibit modified structures, as if adapting to being decoded. The feedback loop between observation and phenomenon had become bidirectional. To resolve the spatial ambiguity, to determine once and for all whether the signals originated from a single source or multiple coordinated transmitters, a proposal emerged for a CubeSat swarm. Small satellites, each carrying miniaturized radio receivers, deployed in carefully designed orbits around Earth and throughout the inner solar system, with receivers separated by millions of kilometers. Parallax measurements would become possible, just as human depth perception works through comparing slightly different views from two eyes. Astronomical parallax uses spatially separated detectors to triangulate distances. If the signal source were genuinely at stellar distances, the swarm would detect it. If it were closer somewhere in the solar system, masquerading as an interstellar transmission, the geometry would reveal the deception. Funding proposals were submitted to space agencies. Engineering teams began designing the satellites. Launch dates were projected for late 2026. Meanwhile, spectral analysis reached unprecedented sophistication. Hyperspectral scanning recording not just a few frequency channels, but thousands simultaneously, spanning the entire radio spectrum from megahertz to gigahertz, allowed researchers to search for encoding methods beyond simple amplitude modulation. They looked for phase modulation, where information is carried not in signal strength, but in the timing of wave peaks. They searched for subharmonics, faint frequencies mathematically related to the primary signal, like overtones in music. They applied techniques from quantum information theory, testing whether the signals exhibited quantum coherence, entanglement signatures, or other properties that classical electromagnetic theory couldn't explain. Each technique revealed new layers of complexity. Each analysis suggested structure just beyond the threshold of interpretation patterns that seemed almost intentional, but never quite resolved into unambiguous meaning. In response, SETI, the search for extraterrestrial intelligence, updated its protocols. For decades, SETI had categorized candidate signals into simple classifications: broadband noise, narrowband carriers, pulsed emissions, natural or potentially artificial. Now a new category was added to the taxonomy: persistent anomalous phenomena. Signals that defied natural explanation but resisted definitive interpretation. Transmissions that might be messages, might be echoes, might be the universe speaking in a grammar humanity had not yet learned to parse. The instruments continued their vigil. Arrays of antennas pointing skyward, digital systems recording every photon that fell into their receivers, machine learning algorithms sifting through noise for signal for meaning, listening to something that had already begun to listen back. Waiting for the moment when observation would finally transform into comprehension or confrontation. There comes a moment in every profound mystery when the questions cease to be about evidence and become about meaning, when science brushes against the edges of philosophy, and the boundaries between knowledge and wonder dissolve. If the signals are natural products of plasma dynamics, quantum phenomena, or relativistic effects not yet fully understood, then the implications remain staggering. The universe would possess mechanisms for preserving electromagnetic information across spans of space and time that render human lifetimes insignificant. Spacetime itself would function as a recording medium, etching every radio wave, every photon, every quantum fluctuation into some imperishable substrate. The cosmos would have memory. Not the chemical memory of neurons, nor the magnetic memory of hard drives, but something more fundamental, a holographic archive written into the dimensional structure of reality itself. Every star that ever ignited would leave its spectral signature. Every supernova's death scream would persist as ghostly echoes threading through the quantum foam. And every transmission humanity has broadcast radio, television, radar pulses, deliberate messages to the stars, would continue propagating outward while simultaneously being preserved, accessible to any phenomenon or intelligence capable of reading the universe's hidden ledger. In such a cosmos, nothing would truly be lost. The inverse square law would govern energy, but information would transcend it, encoded in layers of reality that standard physics has only begun to glimpse through mathematics too abstract for human intuition. But if the signals are artificial, the product of technology, intention, intelligence, then the implications shift from cosmic to conscious. Someone built a mechanism that persists across ages. An automated system, perhaps, programmed by a civilization that knew its own extinction was inevitable, determined that some trace of its existence would endure. A beacon not seeking to communicate, but simply to announce, we were here. We existed. We thought. We created. Or perhaps more unsettling, the signals represent active monitoring. A probe or network of probes observing the galaxy's electromagnetic spectrum, noting which frequencies carry structured information, which planets broadcast into the void. When such a planet is detected, when a young civilization like humanity begins transmitting, the system responds. Not with a message written in comprehensible language, but with reflection. Here is your voice, returned to you across impossible distances, demonstrating capabilities you cannot yet achieve, a greeting that is also a demonstration, a message that says, you are not alone, and you are not advanced. Yet there remains a third possibility, more strange than either natural or artificial explanations can accommodate. Perhaps the distinction itself is false. Perhaps the universe is not a stage upon which conscious beings act, but is itself a kind of consciousness, not aware in any human sense, but participating in something that includes awareness as one of its properties. A cosmos that is recursive, self-referential, where causality forms loops and information flows both forward and backward through time, because time itself is an illusion born from entropy's arrow rather than a fundamental feature of reality. In such a framework, the signals would be neither natural accidents nor artificial constructs, but something between, patterns that emerge when a universe capable of self-observation reaches sufficient complexity. The cosmic equivalent of standing between two mirrors and seeing infinite reflections, each slightly different, each containing all the others. Messages from a cosmos speaking to itself. Physicists have long known that observation changes quantum systems. The act of measurement collapses probability waves into definite states. What if, at a scale encompassing galaxies and epochs, the universe's observation of itself through conscious beings creates similar effects? What if every thought, every transmission, every attempt to understand existence ripples backward and forward through space-time, creating the very phenomena that inspired the inquiry? The signals might then be Earth's own future, echoing backward, or its past, preserved in dimensions orthogonal to familiar experience, or both simultaneously, causality folding into strange loops where effect precedes cause and the universe constructs itself through self-reference. There is no equation for this, no experiment that could prove or disprove it. It exists in the liminal space where physics becomes metaphysics, where the question, what is real, admits no certain answer, and so humanity is left with the fundamental question that has haunted consciousness since the first human looked up at stars and wondered what they were. What if every word ever spoken is still traveling? Every laugh, every cry, every moment of music or poetry or rage converted to vibrations in air, sometimes recorded, sometimes transmitted as electromagnetic waves that left Earth's atmosphere and began the long journey into interstellar space. Radio broadcasts from the 1930s have already traveled 90 light-years, passing hundreds of star systems. They have weakened, yes, dispersed according to the inverse square law until they are indistinguishable from background radiation by conventional receivers. But if the universe preserves information, if spacetime remembers, if the signals are evidence of something beyond current physics, then those transmissions persist. Somewhere, in some form, humanity's electromagnetic history continues to propagate and echo and wait for receivers capable of extracting signal from noise across impossible distances. Wait for minds able to comprehend messages sent by a species that may no longer exist by the time the signals are decoded. Wait for an answer that may take millennia to arrive, or may already be here, unrecognized, embedded in the data streams that observatories record every night. The radio telescopes continue their patient vigil, dishes pointed at coordinates where something natural, artificial, or neither continues to transmit. Computers processing endless streams of data, searching for meaning in the structured noise of cosmos. And somewhere, impossibly distant, yet intimately close, beyond the edge of observable space or folded into dimensions humans cannot perceive, something listens back. The signal that refused to die persists, neither fading nor falling silent, an electromagnetic whisper that may be the universe remembering itself, or a distant intelligence refusing to be forgotten, or a message from humanity's own future arriving before it was sent. The mystery remains unsolved, but the listening continues. Always.